All right, I think we'll get started here. So, good morning, everyone. My name's Ryan Walker. I'm a network engineer at the National Center for Supercomputing Applications, and spend part-time as a network engine or as a security engineer, sorry, for Fabric. How many here are familiar with Fabric at all? Ish. I'm going to spend a little bit of time uh, kind of giving an overview of it, so uh, we're kind of on the same page. I admit these first overview slides are not my own, so I don't have in-depth knowledge, but I think it's good to look through them really quickly and understand what the purpose of the experiment is. At base, it is a series of OpenStack nodes distributed all across the US and some in Europe and Tokyo, where they have resources that are programmable through kind of a number of different ways, interface and API that the Fabric team has built specifically to kind of be a meta controller for all these different OpenStack instances. They have many different resources available, definitely compute and programmable network at each individual location. Some sites have additional resources like extra GPUs, FPGAs, additional storage, things like that. They are all connected via high-speed networks with a terabit ring connecting the main sites. We'll see that network topology here in a bit. But fundamentally, that's what it is. It's all these resources where experimenters can come in and programmatically set them up in different ways to enable whatever sort of experiment they might like to do. Why Fabric? I'll just kind of let you look at that. From my perspective, I'm on Fabric because they needed someone with network experience to come do security. So that's why Fabric for me. But we have a lot of experimenters who are using the resource for many different reasons. Many key features, but they're not too important to this talk. Here's a collection of some of the different partners involved. So it's this will be important because that's a lot of different people, right? And given the nature of this distributed experiment, that's a lot of different hands that are involved. Here's the topology I mentioned. The yellow is that terabit core. All the others, I believe, are going to be 100 gig or multi-100 gig in here. So it's a pretty high bandwidth network, pretty distributed. Let's see. I'm from NCSA, which is here, and they have written there, down there. But yeah, there's a lot of different features here that you can see. There are other sorts of connections where Fabric connects to other experiments, and so you can utilize things like Chameleon across the Fabric network, to different sites. We connect to AWS and some other partners. There are 33 of these different nodes that I mentioned. Here, this is kind of talking about some of the stuff I already mentioned, but that 33 number is going to be kind of a lot and going to add some additional challenges for the network security. Here's some specifics on some of that hardware that we mentioned. And this is interesting. So this is kind of this is an overview of an individual site, kind of a generic one. It doesn't have all of the features of all the sites. But you can see here, they have the different resources that are available to the experimenters. And then there's supporting infrastructure that we need to make them available and to administer everything there. Here's some of the network services. These all kind of run over the network in a way that we don't have to worry too much about these, but I will point out the FabNet v4 and the FabNet v6. That is actually how we can enable experimenters to talk outside of the Fabric network to the wider internet. We review every request to have those. So, everyone can't just, sign up for a free Fabric account, get associated with an experiment and then start, spamming the world, right? We don't want that. But we do have to be mindful, though, that people can still talk out and listen also to outside communications. Here's just kind of a standard rack. So at a site, we will have our own rack that has all the different hardware in it. This is a pretty standard one. We have some that are full top to bottom, basically with only 1 or 2 U available. I was tempted to put in a network diagram or a cabling diagram rather as well. But that was just a little too messy for the screen. Here again is kind of the external connections. Here's the different facilities, like I mentioned before, the different experiments and stuff that we can connect to: Chameleon, Cloud Lab, those fun things. And here's a little bit more on some of those different things we connect to. Fabric has a few different ways of interacting with it, of setting up your experiments. The one I think we push for most is Jupyter Hub. That way, all of your experiments are reproducible, shareable. We have Kubernetes cluster set up in Google Cloud that runs Jupyter Hub for anyone who has a Fabric account and is associated with an experiment. This is great for students. We have a lot of students who will come to a conference and Fabric will set up a temporary experiment for them, or instructors will utilize this for a class. That securing that is also a different challenge. Not so much. I'm not going to talk about that too much, but I'll refer you to Koppel's previous talk. We also have just a general API. That's actually what everything uses ultimately to connect to Fabric. They have built their own API and present that. There's a Python library that you can get for coding against the API directly. The Jupyter notebooks that they have use that same library to connect. There's a command line interface, which is a wrapper around that library. But it's pretty flexible for different kinds of experiments that way. All right, and now focusing on the network security. I mentioned the public v4 and v6. That is multiple 100 gigs, and we definitely need to be able to secure that. We need to be able to see what's happening on there. We want to be able to block traffic from coming in or coming out, right? We have our own reputation to maintain. It's not going to look good for experimenters if people say, "Oh, I have Fabric, it's a bunch of spam coming out," and they say, "Oh, I used Fabric for my experiment." Just wanted to refresh that. So the complexity of securing this is it was almost overwhelming, right? But we were able to work on it and get it kind of constricted in a way. You see the cloud up there coming out of Chicago. Initially, they were going to connect to all of those sites, and they still do have these connections at multiple geographically redundant locations. I'll get into this a little bit more later, but when it comes to securing that kind of high bandwidth network connection, there's going to be certain physical tools and tooling that you need to do that. And we're pretty constrained in, first of all, being able to buy equipment, but even if we could afford enough equipment at all the different locations, power and cooling are going to become an issue, and space. Here again is the node. We need to be able to secure these individually as well. It doesn't really show here too much. It shows that they have this data plane connection, which is that high-speed experimental network. But the researchers also need a way to get in, manage their experiments, get them set up, pull in their Docker containers or their data sets, from their home institution. That is done via what's called the management network. The naming can get a little confusing here because it's kind of management from the researcher's perspective, how they interact with stuff. We also have what we call the operations network, which is how the Fabric admins actually do the management of the resources at each site. Those networks are provided by the site that we connect to. So we want to be good stewards of that IP space as well, because we don't want to affect the site's reputation. So here's an example, say site one that has also those other networks that I talked about, operations network, management network. You can see they're on a different AS with different IP space than we have here in the data plane. Of course, we have multiple. Here's site two. You can see it's a different IP space for management and operations, although data plane still stays the same. It's the Fabric PI space. And we iterate this 33 times. We have 33 different sets of subnets for operations and management that we need to be aware of. We need to have we have to be able to see what's happening there. We have to be able to stop bad actors, both egress and ingress. This shows only the example v4 subnets. A majority of the sites provide two v4 subnets and two v6 subnets, but that varies site to site. Some sites are only v4, some sites are only v6. That presents some challenges when we try to build out some of our observability tools that we'll talk about in a little bit. Now here's the original, when I started, which was just before the end of the construction of the experiment. This is kind of the security design they had. For the sake of the network security, I'll point out they just had a few ACLs. Kind of firewall ACL stuff at a few key locations. But that was about it. And I don't know if you're very familiar with ACLs, but they don't provide a lot of observability. I mean, at best, you can see how often the ACL gets hit. And so you can have a count, but beyond that, not too much. But with well-built ACLs, you can actually do a pretty good job of preventing traffic that you don't want. So these are written to restrict, for the operations network, you can only connect from the other devices on the operations network, the VPN and whatnot. Management network incoming will only talk to the Bastion hosts that they set up. So it's a pretty hard outer shell. But again, it doesn't have everything that we want as network security people to really get our job done. I will also note that they had, as part of the original design, they'd have site monitoring with Zeek that runs on the OpenStack head node as a container. They hadn't really fleshed out that design, but it's going to be good for us that they had planned to have resources available for that. We're actually going to leverage running that container. But I'll note that if you have 33 individual Zeek standalone installs running, it gives you, pretty good insight into what's happening at that one particular site. But it's going to be really hard to correlate what's happening across all of the experiment. You'll have, 33 different con logs, 33 different notice logs that you'd have to somehow integrate if you're going to do any sort of security analysis or, incident response. Also, those were a span from the switch that connects to the management network. So I don't know if people are too familiar with it or care too much, But if you span traffic, you're taking, basically you have 10 gigs out and 10 gigs in, and you're spanning that and pointing it at one interface and saying, I want to combine that and go out, and it's only 10 gig. So you can very quickly overrun that connection. Unfortunately, that's just kind of a limitation in these cases we'll probably have to deal with, but it's a risk that we need to be aware of. So based on that initial kind of security design, what do we want for network security? Well, we want to be able to identify the people who are connecting in. If you're only spanning that one interface on the management traffic, you're going to see all these great SSH sessions coming from the Bastion host. So the Bastion host is always going to be your source IP. That doesn't really help us identify who it is. I mentioned this before, but we'd like to be able to correlate logs across all the different sites. If someone were to decide to attack Fabric, it's not too hard to find out what those different subnets are for the different sites. They could easily start scanning across them. And if you were to do it in a not too unclever way, if we had individual sites, Zeek logs would never they would never notice there was a problem, right? One connection here, one connection there, not a big deal. But if we correlate that across all the different ones, we could easily see then a pattern if there were one. We'd like to have some network security automation, some ability to respond if we're getting scanned on the data plane, say from outside, someone's attacking people's research instances. We'd like to be able to block that. Not just see it, but respond. So to do that, we have to monitor the data plane as well. And the only configuration we've seen right now only monitors the management interfaces. And yeah, like I say, we want to be able to block that via the automation. So again, with the identifying who's SSHing in, this actually, I guess this is all the stuff I kind of talked about. All right, but so how do we then address that? For that first one, who's SSHing in? One thing we could try is if we had a seam, we could try to correlate the Bastion host syslogs with the Zeek con logs or the Zeek SSH logs, but that gets a little bit difficult, and that's a lot of overhead for a pretty small security team. Also, we didn't have a seam that we could use to do that. I did find out later that we have a small elk stack that is used for collecting a certain logs from the API, but that is actually pretty overrun, and we didn't have access to it. So perhaps we could do that, but we ended up with other solutions. One of the solutions we identified is if we had visibility on the outside of the Bastion as well as inside of the Bastion, then we will actually see the actual originating IPs from people. If we can feed that into Zeek, then we'll have all of that information there ready to be responded to, ready to be analyzed. But to do that, we need some hardware. Optical taps to get around the problem of spans, like I said, and also because most of these connections are optical anyway, passive optical taps is kind of the way to go. It also minimizes the amount of power that we will need, but we still have to, plug that in somewhere. I will also point out that the original Bastion hosts that were being used were VMs in VMware infrastructure at Rensselaer and Kentucky, but they were outside of Fabric's management. They were just managed by those institutions. They said, here, you can have a couple VMs. Trying to get traffic visibility inside VM, unless they're paying for special VM features, is kind of difficult. And also, this was, again, outside of our administrative domain. So instead, what we did is we bought a couple of Bastion hosts and distributed them geographically. Also, the VMs were not really able to handle all of the SSH traffic that was being generated. Hopefully they've been able to fix this some in the code, but when you're using, Jupyter Hub or some of the libraries to make connections, they actually would just create a new SSH connection for every command that needed to be sent in and leave that connection open. And so the VMs were kind of getting overwhelmed by that amount of SSH traffic. But then we had to decide where we're going to put that hardware. I mentioned, space and power constraints. We also, though, have a mix of site capabilities. And so we're going to use that to weigh in to where we're going to put those. But there are a few more considerations before we decide. As far as the log correlation, again, I mentioned the problems with having, standalone 33 different standalone instances. So what we decided to do was build a Zeek cluster. If anyone's familiar with Zeek, you're probably familiar with clusters. One thing you might not be familiar with, because I'm not aware of anyone else ever having done it, is having a widely distributed cluster. So in this design, each one of the sites, the container that's working would now just become a worker node. So it doesn't have the overhead of logging, management. So we're able to process a little bit more traffic that way. And then it sends all of its logs to the centralized manager, which, actually does the log management and analysis. Of course, I did mention each one of these sites has a whole different set of IP space. That gets a little unwieldy to manage, but again, in the cluster configuration, all that means is a little bit more complex of a node config. There were some worries when we proposed this design that when other places have tried doing distributed clusters in a way, they had a lot of problem with losing traffic information because of asymmetric routing and issues like that. Luckily here, because we have so many different subnets, we're not really going to have so much asymmetric routing, right? Everything has to come in and out of a single site, and it's going to have that IP space. We'll have that visibility. Even if it comes back in to another node via that path, via a path, at each worker, it will still see both sides of the traffic. We'll have a complete view of what's happening, maybe a little bit of duplication. So with that traffic analysis, we felt pretty confident we could move forward with this cluster configuration. It looks like I missed a little something here. But so for handling all of those logs coming in and for the tapped traffic, we're probably going to want some hardware to be in that cluster as well for the manager, and actually for a couple of workers as well, which we'll see. Because we also want to monitor the data plane, like I mentioned, and that's multiple 100 gig connections. A Docker container with a 10 gig NIC that we can span to is probably not going to handle the traffic from multiple 100 gig connections. So that's another reason why we wanted to get hardware. We also had multiple peering sites, like I mentioned, for redundancy. That we weren't able to get enough hardware, and some of those peering places didn't have power or space for hardware. So there we changed our routing policy to prefer the sites that we could physically tap. If something were to happen at that site, though, we would fail over to a non-monitored site. That's a known risk, but that way the experiments could continue, and then we would just lose visibility until we're able to recover. Because we have multiple 100 gigs, though, we also are going to need an aggregation layer to manage that traffic coming in. So the way a Zeek worker node works is it needs to be able to see both sides of a TCP session, source and destination. And in order to ensure that, you have to make sure that both sides of the conversation are coming out and of whatever you're using to get the traffic and going into the worker on the same interface, because an interface is associated with one or more CPU cores to actually do the processing. And if you're not able to manage getting that traffic into the same interface, Zeek is going to say, hey, I see asymmetric stuff. I only see one side of a TCP session. I don't know what's going on, and start throwing errors. In order then to do that, you need what's called tap aggregation layer, which has a feature called symmetric hashing. So may or may not be familiar with hashing functions on networking gear, but say you have redundant 10 gig connections between two devices that you're sending traffic through. The way the network gear handles that, deciding how it's going to distribute the traffic across those two paths, is it just takes a hash of, source and destination, or source address, source IP, destination address, destination IP. There are multiple different ways you can hash it out. But then it'll use that to choose, send it here or here just to distribute the traffic. But we have to force it so that our n tuple, probably a 4 tuple here, source address and IP, destination address and IP, will hash to the same hash, just whatever the order, right? So destination IP, destination port to source. Of course, I mean, it's still source and destination, but basically, so whichever direction the traffic is going through the networking device, when it gets tapped set to the aggregation layer, it will know to send both of those sides of the TCP session out the same port to the same worker. That takes some specialized hardware. I'll get a little bit more into that later. We also want to be able to block malicious attacks. One of the things that was found with an early engagement with Trusted CI was, in order to block that malicious traffic and to stop spoofing, they recommended we enable unicast return path forwarding. That, unfortunately, I think if the configuration possibly changed after that engagement, or they didn't fully understand the issue, but that would not have worked for what we wanted, because we're actually just taking default on all of our peerings. And the different management interfaces were all just kind of had a default path out. So the gear wouldn't have a way to choose whether or not it should see the traffic there or not. It's basically just a free for all. But we still want to make sure that we prevent our users from spoofing traffic. So instead, we created anti-spoofing ACLs and applied those, figured that would meet Trusted CI's recommendation and accomplish that one common method of malicious traffic coming out of Fabric. Another thing that we would like to do to block malicious attacks is null routing, or what's originally called black hole routing. That is something that is enabled actually by the URPF. So we still turned it on, but even though it wasn't doing the actual anti-spoofing, and some routers, including the ones that we have, that enables you to actually check a special route table called the null route table. And when it's making its URPF decision, we'll check that table as well. And if there is a IP in that table, it knows to just drop the traffic, not forward it on at all. And it can do that at line speed, just as fast as it can do any other routing. We can block that. In order to integrate that, in an automated fashion, though, we are going to have to build some new code. We haven't gotten there yet. I mentioned that we were going to have to decide on the sites. So obviously money is a factor, so it can't be too many. Our biggest limitation we found were those peering sites, right? And because of the 100 gig there, we're going to have to put some hardware there. Luckily, one of the sites at Starlight in Chicago, Illinois, had enough space and cooling for us, and it was one of the main peering places. It also had enough for the bastions, for one of the bastions. So that was kind of a natural place. We could minimize the amount of the like tap ag gear and taps that we had to buy by putting it all there. The other location was NCSA. It was, we had space, cooling, and local hands. I was able to go install that myself. We didn't have to worry about teaching other people how to do it. Preferred hardware for this kind of build out. And this is my preference, but I think it's pretty generally held across R&E who build out this kind of infrastructure. For that aggregation layer to do the symmetric hashing and handle the traffic, we prefer Arista hardware. And then the Dell, R600 something or the equivalent. I don't have the information off the top of my head, but there is a kind of a formula that you can apply. It changes over time, but that you can, I think, Zeek developers can provide for you with how much traffic a single CPU core can handle. I think it turns out to be on the order of 3 to 5 gigabit per second per core. But I think the recommendation that I last saw is you want to make sure you have at least a 3 gigahertz processor so that when you're so you can handle enough traffic. And then we want to make sure that we have network interfaces that can take in that traffic and apply the right kind of programs that Zeek will apply to handle it and make some routing decisions. And that was recommended as the Intel 700 series NIC. Unfortunately, because this was the idea of having network security was kind of put off until the last minute, and we were in the middle of the pandemic at the time. Some of these hardware resources were hard to get, so we had to settle with a Dell kind of beige box switch running NetScout. It actually have the features of doing the symmetric hashing that we needed, but other than that, it was pretty much an unknown entity. And there's no existing code that I could find that integrates Zeek with that API in order to I put here bro BHR, but actually it was the flow shunting that we would want to leverage with that. Flow shunting, I think I talk about this later, but it helps minimize the amount of traffic that we need to compute by when Zeek analyzes the traffic. It recognizes that it's a flow, and then if it recognizes it's a big download, it gets to a gig or however much, it will decide, hey, I don't need to be processing this. I don't need to look at this any longer. The best way they can do that while conserving local CPU is actually to send an API call to the aggregation layer and say, hey, temporarily put in an ACL on this interface to block this n tuple of traffic so that it gets blocked at the aggregation layer. The Zeek cluster no longer sees it. You free up a bunch of CPU. Unfortunately, at this time, we don't have that, and that's another known risk. We did get good worker hardware, though. So here is kind of the physical and logical combined topology that we have. based on those constraints and our wants. It's kind of a mess. I apologize. I've had to try to explain this many times, and depending on your familiarity, your background, different parts will make sense and different parts won't. But you can see what I have here is the provider switch. My cursor is not in the same place on my screen as it is up there. That's the going to be like the management switch at each site. The idea there, so we have the hardware bastion. You know, this is one particular site. You can see all the traffic in and out here. Oh, I'm sorry. No, the provider switch is actually the site switch where we appear. This is the management switch. So we have the tab here as well for any of the traffic that the experimenters are using in and out. You know, if they are pulling from a Git repo, we want to be able to see that. We'll be able to see it here. If someone's SSHing through the bastion to the local site, we'll still be able to see it. This is, you know, Star, for instance. They have a hardware worker, so we'll take in that, the data plane peerings, be able to send to the manager, which is also at Star. One unique thing with our design, our manager hardware is actually extremely beefy, like the worker hardware, more than is needed for just a manager. So we actually have some worker processes on here as well, and some of these, some of this tab's traffic is going into the manager as well. Here is an example, you know, the 31 other sites that don't have hardware, where we are actually leveraging the container with the span. Again, it's a known risk that we're probably going to lose traffic sometimes because of that, but we figure it's worth it for the majority of the time we will be seeing that traffic. And then this is NCSA here with basically the same thing as over here, but without the manager. And here, a new addition to our security design is when we have these logs here, instead of having to monitor them there, we're actually sending them to OmniSoc, who has a SIEM and are better positioned to do the initial analysis of that traffic for us. Here's a little bit more detailed topology. I just chose Star because it was kind of the more interesting one. This has or the physical connections. So that's, you know, going out to, you know, to the rest of the site or the internet or whatnot, comes in, and we have the tabs there for the bastion hosts, data plane connections, etc. And here's where we would like to have that API call to do the flow shunting, but unfortunately it doesn't yet exist. So I think I probably mentioned a lot of challenges already. A little bit more into, you know, how to deploy it. So we had the hardware, we figured out where we have to put it. How are we going to get it in there and wired up? That's kind of a challenge with a distributed experiment like this. We didn't have anyone physically in Chicago. I chose NCSA for one of the locations because I was physically there. We got that handled. But, you know, we sent the equipment to Chicago, they received it, and they said, hey, what do we do with this, right? And a personal challenge, I don't have the experience writing out detailed instructions to remote hands in as much detail as they would need using the language that they're familiar with. The admins on Fabric are actually very talented. They've been doing it for a long time. They can write those up very well. But the knowledge of kind of how this should be configured is in my head, and I was having difficulty communicating to system admins how the network part is supposed to work and how we should how we should instruct them to set it up without me telling them exactly what would be put into the change anyway. I'll also mention I am only part-time funded on this project, so that would be a long time to have to write it out. Luckily, Chicago's not too far away from where I'm stationed. And so I just went up there one day and installed it. That said, after installing it, there were some topology changes that had to be made, both to meet our needs and because of re-understanding what some of this resources that we were given at that site were for. So we had to basically re-IP things a couple of times. We had to rerun cables so that we could drag VLANs around in different ways. But that all adds time and complexity to the project, and that was a difficult challenge to overcome. And additional things that are going to have to change. So I said that the Docker container as a Zeek standalone instance was in the original design. One thing that wasn't in the original design was actually having that spanned traffic connected to the head node so that we could run a Docker container. Not a huge difficult change, but there's 31 different sites this has had to be done at. And though most of the sites are similar, they're all slightly different and would need a different variation of the instructions for the local hands to make that change. We're still working on getting that rolled out. Yeah, speaking of hands-on for that, even if we write the best change procedure, it can be difficult to get access to people's limited personnel resources at these different sites. A lot of these places are research organizations similar to NCSA or probably where you're from. And they're not overly staffed. And a lot of people are wearing a lot of different hats. So sometimes contacting the right person, it's difficult to find them. And once we do, it might take a while for them to get to it. And we have to keep track of what changes have been made to what places. That said, though, all of the local hands that we've interacted with have been great, taking care of us. I don't have any complaints about them or what they've done. I do want to thank them all for everything they've managed for us, but that's still challenging to coordinate and deal with. Bandwidth. There's a lot of bandwidth on Fabric. So I think I did a calculation and it was at least 530 gigabit per second of traffic, potential traffic that we would have to monitor. So 200 gig and 33 10 gig interfaces. And our available CPU can't quite handle that. And we don't have the flow shunting that we would like. So that's, like I say, but right now, all we can do is kind of accept that as a known risk. We don't believe that we will be overrun a majority of the time, but we do have to be aware that there's going to be times where we lose that visibility. I mentioned hands on-site personnel, but other challenges we've had are security personnel. Again, the funding for security, you might be shocked to find out, was not included in the original design of the experiment. I think that's actually pretty common, a challenge that we all face. But we were able to get some, but then we had to, find personnel. They were being brought in late. I, for instance, was brought in pretty late, and I had no idea what Fabric was or how it was built. So it takes a lot of time to learn all the stuff that we've seen and plus a lot more to where we can start just thinking about the security and the network security critically and understanding it. We've since been able to bring in more personnel and we're starting to feel pretty good about our ability to handle it. But that took a while to grow. And another big challenge is there's more to security than network security. I mean, this is a pretty big project with a lot of moving parts. you know, though I was, full steam ahead on the network security design and build out, what happens when there's an incident? Well, we have to bring in the security person. Okay, so dealing with incidents is a challenge, but that, when dealing with the incident, you say, okay, why did this happen? What was there a policy that was violated to cause this incident? We don't have policy. Oh, well, we need to make sure we have security policy. Let's start working on that as well. Policy implies we're going to have security controls. Do we have controls yet? No. Okay, we got to start building those. One of your controls is probably going to be vulnerability management. Do we have a way to accomplish that? Okay, let's start working on that. Vulnerability management is probably going to point to the fact that, we need patch management to address some of these vulnerabilities. Okay, well, do we have a patch management schedule? No. Well, okay, let's start working on that. What all do we need to patch? Okay, let's look at our assets and see what we have. Do we have a list of all of our assets? No. So that then applies, you have to have risk management, right? Like, we don't know what we have on here. That's a huge risk. We start thinking about that. Okay, well, if we're going to be doing risk management, we need leadership buy-in, and we need leadership buy-in up and down this entire stack. I also want to point out that this is probably, hopefully to everyone here, kind of familiar. These are musts in the Trusted CI framework. But we very quickly ran into all of those. One thing that really helped us is early on, Anita here was engaged with Trusted CI. We brought them in to give their analysis of Fabric, the experiment, and its design. By the time I started working on Fabric, we had a list of things to look at that they were able to help us generate. We also took part in cohort beta with Trusted CI. I was lucky enough to kind of get in on the tail end of that and experience some of it. So we did have, like I say, a good stack of findings and needs for Fabric, and we were able to take that to the rest of the team and say, hey, listen, we have these needs. Money is going to be part of it so that we can address these. And they've actually done a relatively decent job at setting aside funding for security operations for this project. And then, like I say, just being able to leverage the Trusted CI framework there. I can't say it's officially adopted, but we're definitely looking at everything through, Trusted CI framework tinted glasses, which has been really beneficial when jumping in on the deep end of a project like this. With that, thank you for sitting in on this test run through of my talk. I really appreciate it. I am happy to answer any questions you have, now or later. Here's some of the information and how you can get a hold of us. Thanks.
Yeah, we have oh, sure.
One of the things that stuck out to me in your later slide there is about the incident response process, especially as you have 33 distributed sites, and you already talked about how there's a lack of physical personnel at the sites. One of the things that Mike and I have encountered over the last 5 years running distributed security teams is like curating, and maintaining a list of site contacts for incident response is crucial and also impossible. And so, like, have you had any success doing that? Have you been able to work with like other projects? Like, does the I know there's like some other teams that keep collections of security contacts at sites. Are you able to leverage that information? How have you approached it?
I was even luckier when it came to leveraging information. Anita had done a first pass at generating that security contact list at all of these sites, which I think was built from contacting just our general site contacts there. And then Kim, who's another security engineer on the project, has also made sure we keep that up to date. So I think that we're actually pretty well positioned with that site security contact list. A challenge there, though, is responsiveness of the people on that site.
Do you exercise that list, like do tabletops or communication challenges or anything?
We have exercised parts of that list in a couple different ways. Like I say, it's been updated. Kim actually reached out to everyone and verified them recently. And so that was great. But when we try to reach out to them with things like, hey, you have a firewall on your management network and we need it to be changed or opened. I mean, I didn't have that on here, but that's another big thing. All of these different sites have different security of their own. And some sites were behind both a data center firewall and a border firewall. Some sites were just out in the Science DMZ, which is great for me because I kind of consider Fabric to be a Science DMZ anyway. But yeah, I've had to try to reach out to the site security contact list and say, hey, we need you to modify your firewall. We're bringing up this new bastion. People need to be able to get in. Crickets. Still trying to track all of that down so we can get this turned up. But you're right. Yeah, having that site security list is very important. Any other questions, comments, ideas for me, for us?
Yeah, I think this is a great talk, and I think security automation seems very important because the defender is not many of the defender like you and other. So I wonder if the black hole router, part of it can be automated in some way, not only to reduce the load to the Zeek, but also block the volumetric attack and more advanced attack.
I'm really hoping that we can do that. I want to be able to, yeah, as you say, with Zeek, if we can build the tie-in properly, we'll need to have some additional services run in order to automate the black hole routing. But we do have equipment that's able to do it. I'd like to explore ways we could tie that in with OmniSoc in the future once we're in a good position. If their SIEM has any automation capabilities, then maybe we could tie that in with exposed API to put in these blocks. I think that would be great. Challenge there, the routers that we use to peer at these sites weren't sized to handle large routing tables. I actually don't know the full size of the routing table, so I couldn't say how many blocks we could put in. But I know at other sites where I've run similar systems, we're usually on the order of 80 to 180,000 blocks at any given time. So that's a reasonably deep routing table if it's especially in line with your actual route tables as well. Yeah, I'd be interested in any automation ideas that people have for how we could implement that and maybe scale back black hole routing from the traditional way of having so many blocks or for so much time. Maybe there's another way we can look at that, and I'd be excited to address that.
Yeah, I think last point is a disaster recovery or disaster plan, like planning for a ransomware or some like internet-wide routing disruption. Some thought about disaster recovery for Fabric. What is the worst case scenario? Would be interesting. Maybe not on your priority list right now.
No, I mean it's a big worry, but it's also a tough one to address, right? And I think we need to finish building out this layer to give us the observability to see when something like that is coming. My biggest fear is, the sysadmins missed an ACL or misconfigured something, and there's an OpenStack vulnerability that gets released. The recent Linux kernel unauthenticated network RCE, had me sweating a bit. Yeah, I don't really know what we have in the way of disaster recovery. For the network security infrastructure, I think it's a known risk, right? We don't have backups. We don't have personnel at the locations to address issues. We just have to kind of try to route around it or know that we're flying blind for a bit. Anything I missed as far as ways that we could have better visibility on the network or other prime candidates for security automation or other defense stuff? It's another challenge, I guess, is a limited number of eyes have been on this. I have a reasonable amount of experience in more kind of like enterprise and science DMZ versions of the Zeek and black hole routing and whatnot. But there's probably stuff I missed. And I'd be happy to hear if anyone had any ideas or spotted any big holes. If you think of anything, let me know.
What are you using to populate your null routing table today? Where does that list go?
So it's currently a mix of the original Justin Azoff written BHR code and the ESNet Scram replacement. Actually, I don't think we have Scram in production anywhere yet. We're working with them on kind of retooling it and expanding its what's the word I'm looking for? Basically, how it can be built out, how it can be applied. Like it's very specific to ESNet's environment right now, where it's Docker on Ubuntu and that's it, right? You can't do it any other way. We're looking at getting it running under Apptainer on RHEL, which I think is a little bit more, yeah.
Was I making that face?
No, it's right. It's the right thing to do. But at least if we could get it working on RHEL and their inbuilt libraries and stuff, I think it's going to be able to be more widely adopted by other institutions. And having it under Apptainer is, RHEL 8 does not play great with Docker. So as we move forward, having those different options available, I think will make it easier for other places to implement it. So we're putting some resources in there too.
Do you have intelligence feeds that go into that environment now, or is that one of the things, like you mentioned working with OmniSoc on getting some sort of feed? We don't currently do that directly from the scene, but we have feeds that have some of that data. And there's also the Stinger project. It's now called Forewarned. So like a deployed honeypot network that has a list of IPs you can put in that table. And Red ISAC is experimenting with Shadow Server to try to gather more data from higher ed, doing a similar approach.
Do I personally any place have Intel feeds? And some of the clusters that I help manage, yes, and some no.
Like where would you in your current environment, your current setup, you were talking about moving towards automation because now it's not automated. So where are you waiting to see an event in Zeek and then adding it to the table?
That would be step one.
Okay.
And especially considering the limited constraints for how we can do blocking, we would probably have to stick with that. Those Intel feeds are robust, and even throwing away false positives, there are a lot of hosts in there. And so if we were to try to stuff all of those into our route table to block as a BHR, I think would be difficult. We don't want to put a firewall there. I mean, I didn't mention this, but hopefully it's obvious. Putting a firewall around Fabric, especially the data plane, would be a hindrance to the science, right? That's putting latency and a failure point like on the network, and it's supposed to be a high-speed network experiment, right? Also, there aren't a lot of firewalls that can handle that much bandwidth. So. All right, well, thanks again, everyone. Feel free to stop me in the hall if you have anything else you want to talk about or questions or comments specifically about Fabric. I'm happy to talk about it. Thanks.